Okay. Calculator's out, and you should have page 163 out, please. Calculator's out and page 163 out. We good? So we're going to walk through, just starting out the calculator, just know what we're doing, because a few things might be plugged in there that are goofy, which it is what it is. Item 1, you turned it on, yes? Okay, and other things, just do, once it's turned on, go to y equals. If you have anything plugged in there, bless you. If you have anything plugged in there, hit clear. Does anybody have the plot 1, plot 2, plot 3 on? Yeah. Your plot 1's on, so it looks like this? Looks like that. So it's kind of like that right now? Yeah. So move your arrow up to it, hit enter, and then move down. Cool? And then the other thing we're going to do is go and hit zoom and then number 6 for right now. What that's going to do, it's going to give you a negative 10 to positive 10 grid in the XY direction. So zoom, and then the number 6. And it'll make you go from negative 10 to positive 10. So this is just taking it back to, a default mode for you. We good? All right. Let's talk about this first problem. It talks about, so here's this equation. H of t is equal to negative 16t squared plus vt plus s, right? Is that the equation they give you? I will make sure you have that equation. I'm not going to, we can't forget about that. That'll be given to you. So the variables that act like x in this equation are t. They're just using t because we're talking about time. And the problem will define for you if you're using time in seconds, days, years, minutes, hours, okay? But let's go a little bit further on this adventure about this problem. All right, it says use this function for the following problem. The height of an upward projectile after t seconds. So time is going to be in seconds on this problem. Does that make sense? How do we know? They told us we were going to do it in seconds. Okay? Now, things we have to remember. The v value is positive if if something has an initial upward velocity. It's going away from you. Okay? Your v value is negative if you're like standing on top of a building and you threw something downward. That would be negative v value. And if you just dropped something off a building where it didn't have any accelerate or any velocity in any direction, it would have been 0. So your vt term turns to 0 because you have 0 times t and 0 times t is 0. So are we okay so far? So let's figure out what this whole adventure has for us. It says a rocket is launched from an 80-foot tower with an initial upward velocity. Okay, so you have this building, a tower, that happens to be 80 feet tall. Now, that 80 feet is our starting point. That's our S. Okay? If you're starting from a higher object and it's going to get to a lower object, your S value is going to be positive. Okay, so in this case, we're starting at top of an 80-foot tower, and then we'll come back to the ground. So should our S value be positive or negative? Negative. So we're starting up here, and it's going down. So we're starting from a higher object, a higher location, and going to a lower location. Negative. It needs to be positive. S has to be positive. This is positive 80. Okay, now the only time this S value is going to be negative is if I were launching down here and I was getting it to land on top of this. So I would be underneath where it would wind up. We good so far? Yeah. Okay, the negative 16c squared is going to stay as is for right now, plus we're going to have a t value, and we're going to plug in for v. So let's read a little bit more. It says, a rocket launched from an 80-foot tower, got that, with an initial upward velocity of 212 feet per second. Okay? So is it positive 212 or negative 212? It's Positive 212. So this is our equation that we're going to use on our calculator. Y equals negative 16t squared plus 212t plus 80. And again, the t's are going to act just like x's would act with our parabola. We good so far? Now, this is a starting point. This is a real equation. This is not, we didn't just make this up. We didn't say, oh, wouldn't it be cool if. This is real. Okay? This is where those really cool people at NASA or for any of those other companies that are launching things into outer space, this is one of their primary equations. If you were to walk in and see their board, you would see this equation up on their board. Okay? So, like, this is a starting point. Now, there's some really cool complex ones out there. This is a really cool equation. So let's talk a little bit. We're going to come back and work this problem a little bit, but let's talk about a few things that are absolutely amazing. Okay? So, I don't know if you realize this or not, but astronauts that go into outer space and spend a significant time in outer space, when they come back to Earth, they're actually younger than they left.
They look younger?
They are younger than they left. That's exactly what I said. So let's talk about how that even works. Okay, let's talk about something that's called the twin paradox. So Earth, still with me? And let's say twin number 1 is hanging out here on Earth. It's kind of broken body. Here's twin number 1. Okay? Twin number 1 sitting here on Earth. Now we're playing this cool looking game. Make sure I can get lined up again. I think I won. All right. Let's say this twin on Earth has a light bulb on top of this little platform, and this light bulb turns on and off every 1 second. So it turns on, it's on for a second, turns off, it's off for a second, turns on, it's on for a second, turns off. So that person's standing on our Earth, and they're standing at the North Pole. So when we fly away from Earth towards the north, we'll be able to see it. Okay, so as that light bulb turns on and off, that person standing next to it is going, it's on, it's off, it's on, it's off, it's on, it's off. Okay, it's constant. They could have a timepiece in there, a stopwatch going, yep, it's still doing it. So let's say this person has their stopwatch and it's counting. Okay? Start. Stop. They had hit start and then it's just counting. Every other second the light's on, every other second the light's off. Make sense? Well, you understand that light will continue and never phases out. Now, it'll become a photon that you can't see once you're really far away from it, but it will always exist. Still with me? Now, let's say this person has a twin brother or a twin sister, and that twin is on a rocket ship flying away from Earth. Okay? They're flying away from Earth. But on this rocket ship, there is a sensor down here, and all it's doing is reading the light as it comes to it. Comes on, comes off, comes on, comes off. Okay? And also on board this rocket ship is also a counter, like a stopwatch. Okay? Start, stop. Okay, so every time the light hits the sensor on the rocket ship, and that sensor is pointed in the direction and theoretically is in the same line of sight as that light is, no matter how far it gets away, because we're talking about it's at the North Pole. Every time the light hits that sensor, the sensor will count up another. Okay, still with me? And as far as this goes, this guy, every time it turns on, this is counting. Okay? So what happens is the light, though it goes in every direction, will be traveling in a wave. And the closer to Earth that this person was, this wave is 1 second in between. I said the closer to Earth for a reason. Because as this rocket ship, let's say they decide to fly and they're going to go this way for 3 months. Actually, let's change it to 3 years. And then they're going to turn around and fly back in 3 years. So you're like, yay! Yay! Coming home. Okay, and as they turn around to come home, this sensor will turn in the direction, so it'll still read the sensor that's blinking on Earth. Still with me? Bless you. Now this is what happens. The further this gets away from Earth, it starts at 1 second, but as it gets further, so as that rocket gets further and further away, light is taking longer and longer to get to it. The person on Earth is sitting there going, yeah, this darn thing keeps blinking every second. The person that's going away from it is going, oh, it's starting to slow down. Well, when light slows down, because you're covering a larger distance, time slows down. So let's say that it was 3 years out, 3 years back. This guy gets back here, and he's like, hey, look, I'm back, yay. And 6 years has taken place. This guy is showing 6 years took place. This guy shows that 10 years took place on Earth. It's called the twin paradox. So you had two twins who were born within minutes of each other on Earth. One got in a rocket, left for 6 years, 3 years out, 3 years back. The other one stayed on Earth. The one who was on the rocket comes back and only aged 6 years. The one who sat there on Earth aged 10. So here's the really hard thing about living on Earth. We feel time is always a constant here on Earth, which it is. Okay? You turn on a light switch in a room, as long as there's electricity going to it and the bulb works, light will turn on in a room. Now, here's the really goofy thing that you have to realize. Y'all have gone outside at night and looked up and seen the stars, right? That light you're seeing from those stars could be hundreds of millions of years old. Meaning that star, three things that are taking place. One, that star is no longer in the location that you're seeing the light come from it. That star might not exist anymore. It might have burned out. And we're still receiving the light from it until it burns out, because that's a couple 100 million miles away. A couple billion, a couple 100 billion. We're talking far. Things are far out. Okay, but as further and further you get, you're talking about, light's only going to travel a certain distance in a year's time. That's called a light year. Okay? So think about the sun. The light that's coming from the sun right now came off of the sun 8 minutes ago. So if the sun burned out 3 minutes ago, we wouldn't know it for another 5. Kind of weird, isn't it? Now, let's take this a little bit further. This is an amazing event. Now let's talk about things that you all should be able to see, and hopefully I'll see as well, is we want to get somebody to Mars. And I would say get a team of people. Now, things that are kind of hard to think about when we go to Mars, everything you bring with you is all you can bring. Okay? And there's going to be a certain amount that's like, okay, you can't bring that too. I mean, the things that would take up any type of volume, weight, or mass has to go into the equation of, do we have enough to get there and back? So somebody who goes to Mars going, oh, I got my ears pierced. Take the earrings out. Can't go. Can't go with the earrings. Why not? There's a certain mass to it. That mass will be weighted into the equation There we go. So you also have to figure this. You have to take all the water and food you would need, but then there's some of the things that we take here on Earth as a luxury. Kind of porcelain oblong shape called the toilet. Yeah, we can evacuate our excrements or our waste or solid movement out into space. It's going to become a pretty much frozen turd. Exactly. But there's other things that you have to make sure you don't take. Your urine needs to go through a distillation unit because that's going to be reused as the water you drink. Dude. I thought I was going. Now I'm out. I ain't drinking my own pee. Not just your pee, it's everyone else's too. It's on the ship. But you think, okay, it's gross. Well, distillation unit. I mean, what do you want to do? You want to create some sort of filtration system that would take. I mean, what is the majority of your urine? Water. So you just have to filter out what's not water, and what do you have left? Water. Now, though it sounds like it's kind of gross, well, I'll just tell you that the water you're drinking coming out of our water fountains or your water bottles has been distilled because that water came with impurities in it, and they distilled it out, and they cleaned it out, so you could drink it. That was healthy. That's kind of weird. But let's say we're going to go to Mars. Okay, you're talking about 3 months to get there. You're on the planet. I imagine they would create something where you would be able to be on the planet for about 10 days' time for the primary. Actually, the very initial first thing will happen is we will have somebody orbit Mars and then come back to Earth. Well, they'll just run some tests on it'll be the spacecraft that they would want to land, but they'll sit there and say, okay, let's mimic what the spacecraft's been doing so far. They'll run through the tests on it. Okay, now, here's the thing that some of you might not know. Let's just talk about 1969. We went to the moon. This is amazing. This is amazing this took place. So this was on a 3-stage rocket. And then you had this mechanism up on top was where your crew was up in here. Okay, you had a 3-stage rocket. So what happened is this blasts off, and this burns, and my times might not be exact, but just go with me. This would go for about 3 minutes. And then what would happen is it actually falls off the rocket, falls back to Earth. And then this stage goes, and this stage starts going, and this might burn for 2 minutes. And then that falls off, falls back to Earth, and then this one might burn for a minute, 90 seconds, out of somewhere in there. Okay? So that means the only portion that's on its way to the moon is this right here. Everything else fell back to Earth. It falls back to Earth, guess what you don't get to use anymore? You're on this rocket, okay, after that first stage of that rocket gets you up to about 36,000 miles per hour in 3 minutes. That's fast. That's more than 10 times the speed of sound. Like you are moving. Now what's really weird is you are strapped into this chair. I mean, you're not just kind of strapped in like, oh, look, the seatbelt has wiggle in it. They're standing on you as they're putting you in, and they're pulling those straps as tight as they can possibly put them. Where you're like, I can barely breathe. Don't worry. It'll be about 10 G's forced upon your body here in a few minutes. So once that rocket launches, all of a sudden you're like, your seatbelt just got loose. It's like, yeah, it's pushing you back in that seat at an unbelievable amount of force. The pants you have on are probably squeezing really tight to keep the blood in this part of your region, from your brain to your torso. Okay, they're some sort of compression pants. So you're moving, you're cranking. So once you get in outer space, well, here's a few things that are cool. So this lunar module kind of looks like this. Kind of looks like that. there's two parts to it. Okay? So this portion here will fly to the moon, but will not land on the moon. The apparatus that's in this region here is the lunar module. So the lunar module kind of looks like this. And so it wouldn't crush. That's sitting in this in an upright position. So when it launches, kind of looks something like that. So when it launches, it doesn't crush. It's on its own feet. But what happens is, in order to get from where the crew is here to the lunar module, a few things had to take place as it went to outer space. This probably opened up somehow, or it opened up in the back. I don't know which one exactly. But this region here is going to detach. So now your lunar module, or this is what's basically taking place. It separates. So what happens is this lunar module has to come out, and it's going to, if let's say it comes out of the bottom, it's going to come out looking like this. Well, here's your airlock here. Here's your airlock here. Okay? This is what's taking place. Let's say you and your friend both have a baseball. You throw your baseball and your friend throws a baseball as well. And you're going to try and get them to connect and hold together while you throw them. Now, is it possible your friend throws a baseball and you could hit it with your baseball? Absolutely. Is it possible to get them stuck together? It's going to be really hard. Yeah, you got to use something to make it happen. So what's going to happen is this object now is going this way. This object now is going this way. You're going at roughly the same speed. So you need to now have this guy catch up with this guy. Not only do they have to catch up, this has to rotate around so it's this way now. Okay, so now, same baseball. Put a dot on that baseball. And say, okay, I'm going to throw, and you put a dot on both baseballs. I'm going to take my baseball and throw it. You take your baseball and throw it as well. We're going to get them both to stick together on the dot. Seem kind of hard to do?
Yes.
Unbelievable. So this has to rotate very slowly because second law of motion is to every action there's an equal but opposite reaction. So with the small little air bursts, they're able to go psst, and they can start pivoting this. Okay? But if you pivot it too fast, it starts tumbling. Okay? So you pivot it, and it's starting to come around real slow. And then as it gets to, say, here, where my pointer finger needs to get there, they need to slow it down. So they're going to take an air burst the other way. A little less air burst just to slow it. Now, you have 3 days to get these two things together because that's how long it takes to get to the moon. This is what's going to land on the moon. There's nobody in this right now. All three of you are sitting in here. Like, la-ti-da, we're bored. So this is rotating around. Now, what these two things are doing, they are now traveling about 80,000 miles per hour through space. So now you need to connect two things together that are both traveling at 80,000 miles per hour. Okay? It's not like a car where you can be like, hey, we're driving. Okay? So these three guys, they have air jets all around on this. And these air jets will allow it to pitch, roll, and gimbal. Okay? There's a lot of stuff taking place there. This has air jets on it, so it's trying to pitch around. So the guys on NASA are really slowly taking care of this bad boy. These guys probably had some frequency they were able to make these work too. But then they were to get these two things to come together. And get them to come together, and then you can go through the airlock. Now here's the thing that kind of stunk. 3 astronauts up in space. 2 of them get in here. 1 stays here. These 2 guys get to go to the moon. This guy just gets to orbit the moon. And stay in radio frequency with those guys that are going to the moon. this equation that we first started with, as I said, that goes with it. Things that change with this is that starts to change. That's relative to Earth. It's not relative to the moon. Did it take as much fuel to get back from the moon to back to Earth? No, there's a lot less gravity on the moon. You didn't need as large of a rocket. You didn't need the amount of fuel, which is great. But multiple things are taking place that we have to be aware of. Okay? That's where this equation starts from. I mean, you have all heard that hey man, I heard we're going to do. Elon Musk launched it. He got a Tesla flying out there. That's cool. But it wasn't just like, yeah, let's see if this works. Hey, you know what? Strap yourself to this rocket. This is what we're going to try. We've done none of the math or physics behind it. We just want to see what happens. I don't know. I might not be too willing to strap my butt to a rocket to try it out. I want to know the math and physics works before things go. What do you think? But this equation is where it all starts. This is just a small seed. Now, I know we've talked about this before, but I will tell you, if we get this whole thing going, when we're going to go to Mars, you're talking about a lot of jobs that are involved in this. I mean, we're talking, yes, you have your engineers, but then you have the people who are scientists that are doing the math behind it, and they're experimenting. And they're saying, okay, yeah, look, this type of thing will give you this much thrust. Oh, okay. Now let's take that much thrust and go back to our drawing boards. Yes, with this much thrust work with this. Yeah, nice thing is it's less amount of space, lighter apparatus, so we can actually use less fuel. You use less fuel, that creates more of an opportunity for you to bring more with you. Wow. That simple equation. That's the start of going to the moon, going to Mars, going beyond. I think that's pretty amazing. Now, did you have to have a PhD in order to work for these companies? No. No. There are technical fields working with this. Someone might have a job that's as simple as, you know what? My job is to make sure that this computer component talks to this computer component at the technical level. Okay, there are things that we've goofed up as humans. That's about 20 years ago, before we had sent those 2 rovers to Mars, we had sent a similar type of thing up to Mars. And you know what happened?
Those all died.
Well, the thing's just gone. They don't know if it crashed into Mars or what. But they're sitting there once they lost the signal going, well, shoot, what happened? You got the one guy going, yeah, well, it's doing 55,000 miles per hour. And you got the other guy on the other side going, you did miles per hour? We did all ours in kilometers per hour. You had 2 people that weren't talking. 2 people that, it was all the right math that was done. It was just one was in certain units of this and one was in certain units of this. What did that mean? It meant that the math was right, but the numbers being plugged in were incorrect. Because one organization was using kilometers and one was using miles. Thank goodness there wasn't anybody on there. Stinking math error. Communication error. So what kind of jobs does that create for people? Hey, you know what all I need to do? What's that? I just need to make sure that these guys and these guys are using the same units. Got it. What units are you guys using today? Miles per hour. Okay, remember that. Right on my hand. Okay, I got it. It's right here. Ooh, a restroom. I don't remember where I rolled my hand. Hey guys, I think they said they're using kilometers per hour. Yeah, I had written on my hand, but then I washed my hand. Cool. Not being sarcastic, but that kind of stuff does take place. There are errors that take place. So there's quality control that has to take place And that's more jobs. There's other people that are going to sit there and say, okay, I need to monitor this specific system while it's flying outer space. I have to make sure that this system is working and doing what it should be doing. And if it's not, I need to start figuring out and bring a team of people in to how we can fix this. Because now you're in outer space, you don't have what you left with. Okay? So, with that, let's go back to talking about this problem. Okay, so we're going to use our calculator. And we cleared this out, and I'm going to use y equals, right? And I'm going to go negative 16x squared, and I forgot, let's see, plus 212x, and then plus 80, because it's at an 80-foot tower, right? So we put our calculator back to negative 10 to positive 10, so it's very possible that we might not see any of our graph. We might see some of it. Oh, I do see some. Looks like a blue vertical line. Well, this is a parabola that opens downward, right? So I'd say this is coming up way up here and way down here. So now we need to adjust the window. And I need to adjust the window in the y direction, and I also need to adjust it in the x direction. So let's do the x direction first. So I'm going to go to window. I'm okay with the negative 10 for the x direction there, but maybe I take this out to 100. And let's just see what happens. If I graph that, oh, I can see both parts of the parabola. Do I still need to go all the way out to 100? No, I could probably bring that in, I don't know, to maybe 30? So I'm just going to bring it into 30. And let's see what happens now. That's closer. I feel comfortable seeing that. So now I have to adjust the y direction. All right, let's go to the window. We're going to make the y maximum. I don't know. Let's go to 1,000. Let's go to 1,000. So from negative 10 all the way up to 1,000. When we hit graph, hey, I can see my parabola pretty well. I did not do the zoom commands because it does distort it. Okay, so that's a pretty good looking parabola in my opinion. So let's start answering these questions. It says find the maximum height reached by the rocket and the time at which it occurs. So if I find the vertex, the x component of the vertex is the amount of time it took to get there, and the y component of the vertex is the maximum height in feet. Okay, so I'm looking for a maximum, correct? So we'll use the same key. So I'm going to go second, trace, and I want to find a what? Maximum, which is number 4, or you can arrow down to it and hit enter. And it says, hey, I want to be on the left side of the maximum. So you have to make sure your cursor is on the left side of it. Is my cursor on the left side of where that maximum will take place? Once that takes place, you hit enter, and then you're going to move your cursor to the right side of it. Am I on the right side of it? Cool. Hit enter. And it says guess. It's like, no, I want the answer. So at 6.63 seconds, after this thing has launched, it's going to make a maximum altitude of 782.25 feet. It's pretty high up there. Kind of cool. If you were sitting in the park and you launched up to 782 feet, your rocket that stands about this tall is going to be real small. So it's still the same size, it's just further away from you, so it's small. Okay, so that's the first answer. So at 6.63 seconds, we get to 782.25 feet. And then we want to find the height at 3 seconds. We want to find the height at 3 seconds. So I'm going to plug a value in. So this is at 6 seconds. That's how high I got. So now we have to go to 3 seconds, and we're going to get up to somewhere in here. Does that make sense? So I'm going to use my second trace command again, but I want to find a value now. So my x value, I want it to be 3. And once I do that as 3, it's going to say at 3 seconds into flight, you're now at 572 feet up. Huh. And you see where the cursor is blinking is where that point is on the parabola. That's pretty cool. And then it says find the time at which the rocket hits the ground. So this is where it's going to hit the ground. So what is this also known as when it crosses the x-axis? A root, which is also called a 0. A root and a 0 are the same idea. Okay? So Now I want to find this 0 right here. So I'm going to use my same command, second trace. I want to find a 0. And then remember with this is you have to be above and below it, or below and above it. So on the left side, it looks like I'm above it, still at a positive. I'm going to continue to move in the x direction, but it's going down. And I have to look when my thing becomes negative. Okay, it's now negative. So I had a positive value and negative value. I don't want to guess. I'm hitting enter one more time. So at 13.62 seconds after it launched, it hit the ground. And that's how these problems take place. Pretty cool? It's not the worst math in the world, I don't think. So I'd like you for next time, I'd like you to work on this, page 165, and I'd like you to do number 4. And we'll go over the other problem tomorrow as well. But then also what's part of this, and I'm going to get you guys and girls this as well, we have the take-home test. Okay? So this take-home test I'm giving to you now.
Is this for the final?
No. This is for the test we have next week. So the take-home test will be due next Wednesday. Now, if this is due on next Wednesday, our test is actually on Tuesday. So I'm giving you an extra day. Now, this take-home test is on Scantron, so you need to find yourself a pencil. So you'll need a take-home test and a Scantron both. I'm not having a work day tomorrow. Monday will be our work day on this if you want to do that, where you can work with each other. So you need one of each. Come grab. And then would you put your calculator, if you borrowed one, back up here in the bin? And that's all I got.